Hello everyone and welcome to CodeGrads. This video offers a comprehensive overview of optimizers, the critical algorithms driving neural network training. We will explore their evolution, mechanics, and selection strategies for machine learning tasks. Our discussion will examine key concepts progressively, from foundational principles to advanced techniques. Optimizers are at the core of training machine learning models, especially neural networks. These specialized algorithms iteratively refine a model's learnable parameters, weights, and biases during training, driven by an error signal from a loss function. Their fundamental goal is to methodically adjust parameters to progressively minimize loss, guiding the model towards better predictive accuracy by navigating the complex loss landscape. With a vast number of parameters in modern neural networks, an efficient, guided search is essential, as finding optimal parameters otherwise would be computationally intractable. Gradient descent, GD, the foundational optimization algorithm, calculates the error gradient across the entire training dataset in one pass. Model parameters are then adjusted opposite to this gradient, moving downhill towards lower error, with the step size controlled by the learning rate. While GD provides a precise gradient, calculating it over millions of data points for each update is computationally expensive and memory-intensive, making it impractical for large datasets in modern machine learning. Stochastic gradient descent, SGD, adjusts model parameters after examining only one training example at a time, significantly increasing update frequency for faster initial progress. The gradient from a single sample is a noisy estimate of the true gradient, but this randomness can help escape poor local minima. The main challenge is the high variance of these updates, leading to an erratic convergence path that may overshoot optima or require careful learning rate tuning for stability. Momentum enhances SGD performance by adding inertia to parameter updates via a velocity term, a running average of recent gradient directions. This dampens oscillations where gradients change sign and accelerates movement where gradients are consistent. Incorporating past step information via velocity significantly alters optimizer behavior, allowing it to build speed, navigate flat regions, and roll through minor local minima, often leading to smoother, faster convergence. Mini-batch gradient descent, MBGD, is a practical compromise between batch GD and SGD. Data is processed in small groups, mini-batches, and gradients are calculated on the average loss per mini-batch. This reduces computational cost, leverages hardware optimizations, and provides a less noisy gradient than SGD for more stable convergence. Mini-batch size is a critical hyperparameter. Smaller batches add noise, but allow frequent updates and can escape sharp local minima. Larger batches offer stable gradients and efficiency, but risk settling in suboptimal minima. Standard gradient descent uses a single global learning rate, which may not be optimal for all parameters in complex models, as parameters can control varied features or navigate diverse loss landscapes. Some parameters need larger steps, others smaller. Adaptive learning rates enhance learning by dynamically adjusting each parameter's step size based on its historical behavior. Information like past gradient magnitudes, directional consistency, and update frequency helps tailor these individual learning rates. Adagrad, adaptive gradient, individually tailors the learning step for each parameter, applying smaller updates for parameters with consistently large past gradients and larger updates for those with infrequent or small gradients. It scales a global learning rate, with each parameter's scaling factor growing based on its accumulated sum of past squared gradients. Since Adagrad accumulates all past gradient information without decay, during long training runs, the sum of squared gradients can become very large, causing the effective learning rate to diminish and potentially halt learning prematurely. RMSprop, root mean square propagation, is an adaptive learning rate method addressing Adagrad's limitations. It adapts learning rates by calculating an exponentially decaying average of recent squared gradients, giving more weight to recent information and preventing the learning rate scaling denominator from growing too large. Using a decaying average, not a cumulative sum, ensures the learning rate doesn't become excessively small, allowing RMSprop to remain responsive and maintain effective learning throughout training. Adadelta dynamically scales parameter updates using a ratio of two running averages, one for recent parameter updates and another for recent squared gradients. This ratio construction eliminates the need to define an initial learning rate, as the step size becomes self-adjusting. While simplifying setup, this automation means less direct control over training, a potential disadvantage. Though Adadelta aims to be learning rate agnostic, its internal decay constants are still hyperparameters, and its convergence may not always match methods with explicitly tuned learning rates. ADAM, Adaptive Moment Estimation, is a highly effective optimizer. It maintains adaptive learning rates for each parameter by tracking past squared gradients like RMSprop and incorporates momentum by tracking past gradients. This combination often yields rapid convergence and robust performance, frequently requiring less manual learning rate tuning due to bias correction and efficiency. Despite ADAM's strengths, SGD with momentum might be preferred if a dataset is well understood, allowing fine-tuned SGD for better generalization, or if computational overhead is critical, as ADAM maintains more state per parameter. ADAM is often a highly effective starting point for optimization due to its adaptive nature, robust convergence, and good performance across diverse architectures with less tuning. SGD with momentum, though needing more careful learning rate scheduling, can sometimes yield models with better generalization. No universally best optimizer exists due to the interplay of optimizer mechanics, dataset characteristics, model architecture, and loss landscape. The best guide for choosing one involves understanding theory, empirical evidence, and systematic experimentation for the specific problem. In summary, optimizers are indispensable tools for machine learning, driving neural network training. We've seen their evolution from foundational gradient descent to sophisticated adaptive methods like RMSprop, Adadelta, and ADAM, each addressing challenges in complex loss landscapes. The choice and configuration of an optimizer significantly impact training dynamics, convergence, and model performance. A nuanced understanding of their mechanisms, strengths, and limitations is paramount for developing effective machine learning solutions.